Hey, my name's Ethan, and today we're going to be breaking down the robots we built for this year's FTC game, POWERPLAY. This year, we brought in 4 guests and split them up into 2 teams to each build their own robot, and they each went through the prototyping, design, build, and assembly portion of their robots during a live stream we did on goBILDA TV. You can check out the archives for that stream over on our YouTube channel and in the playlist linked below. Each of these robots ended up being very different, and they approached the challenges you see in the game pretty uniquely. Our goal for Robot-in-3-Days is always to show you ideas and to give you an idea for how individual parts and robots can interact with this year's unique challenges. It's not to provide turnkey solutions, and you won't find CAD or assembly instructions of either of these robots on the webpage. But we do want to show you how they work and give you a lot of the ideas that were used in the design process of each of these robots. After analyzing this year's challenge, the blue team decided that they wanted to go with a Mecanum drivetrain for its increased maneuverability, but they wanted to make something smaller than the stock strafer chassis. They took a strafer chassis and modified specifically the channels it used to act as its drive rails and crossbeams. They went with a 14-hole long crossbeam, which meant they need to move one of the motors that powers the Mecanum wheels. In this case, they moved the front motors that power the front wheels to be vertical instead of being horizontal like the back wheels are. They also went with a shorter crossbar to make their chassis as a whole narrower. They went with a 7-hole crossbar, and they had a 1120 series full U-channel crossbar and an 1121 series low side U-channel in the back for additional stability. After they decided on their drivetrain and modified it, they went to work on a claw system. They wanted something that was very mechanically simple and required very low power draw in order to work. They started with 2 super speed servos that each drive a servo arm. Now that arm drives a linkage, which is connected to a 45-degree angle pattern plate. That pattern plate is allowed to rotate because it's mounted to a hinge, and on that pattern plate they've laced some surgical tubing to act as some additional grip on the cone. There's also this small angle bracket that can guide the cone further toward the center of the claw. Now they chose a linkage to power this claw for a couple of main reasons. The first being, it's a great way to turn rotation in one axis into rotation in another axis. You can see as the servo rotates, the claw rotates in another axis, and this means they can mount their servos in a very compact way, and one that worked really well for their design of their robot. The other reason they chose a linkage is that it allowed them to create a linkage that over-centers. Over-centering a linkage is when the 2 bars of that linkage end up being parallel. And this means that any force that tries to open that claw, or that exists just because you're putting pressure on the cone, is turned into force that acts against the servo's spline instead of torque that causes the servo to try to rotate. Now, the servo will draw as much power as it needs to hold that position, so the more torque you have pushing against that servo's position, the more power it's going to draw. Because this linkage over-centers when the claw is activated, there's no power that's being asked of the servo, and so it can hold its position without drawing any power from your battery. This also means you can grab a cone without powering the claw at all, which is really cool. They mounted that claw to some low side U-channel, which is mounted to 2 sets of Viper slides. They use 4 stages of Viper slide because it allows them to not have to have an additional vertical extension on the end of their lift, and they use 2 sets to increase the stability of their system. They probably could have gotten away with 1 set of slides here, but they wanted to increase that rigidity, which allows them to drive their robot just that little bit faster. Now they powered one side of those Viper slides. They probably could have powered the other side for a little bit more stability, but they didn't feel like they needed it. And they drove that with this winch pulley that's mounted down in the base of their robot. That winch pulley is directly mounted to one motor, and it has a gear that's driven to another motor. These motors specifically are Yellow Jackets, and they are the 5.2-to-1 gearing that produces about 1150 RPM. Now that cable runs through the system in a continuous routing, much like the 4-stage Viper slide kit, and ends up giving them control over the end of their slide system. As a whole, this robot allows them to drive up to a cone, grab it with their servo claw, lift it up to whichever height junction they decide they need to score on, and release that cone. It's a very mechanically simple robot, and I really love it because of that. On the other side of the fence, we have the Red Alliance robot, which we'll talk about next. I'm sure you can tell by looking at it, but the Red Team's robot is a lot more mechanically complex. It shares some of the same design notes, such as the 2 sets of 4-stage Viper Slide kits, but about everything else about this robot is different. They decided that they wanted to value the increased pushing power and turning speed of a 6-wheel drive, and started with the B-line chassis to achieve that goal. They made a lot of modifications to that chassis. First off, they switched the back wheels from Rhino wheels to Omni wheels to increase their turning speed even more. They also wanted to change the size of the chassis. They made it shorter by using a 15-hole drive rail instead of the stock 17-hole drive rail. And they nested the motors by assembling the chassis differently. So you have 2 drive motors for this side here, and 2 drive motors for this side here. That allowed them to use a 9-hole crossbeam instead of the stock 10-hole crossbeam to make this chassis just a little bit narrower. Building up from that, they used a closer to stock 4-stage Viper Slide kit to create their vertical motion. They used 2 of these that you can see are in their very close to stock form, with some low side channels mounted to the end to create a very easy mounting surface. Unlike the stock configuration of the Viper Slide kit, this slide system is powered by 4 motors instead of just 2 if you had just used 2 slide kits. Now, this allows them to use a heavier end effector, and it allows them to have a faster geared lift than the 2 motors that are used by Blue Team. There are of course diminishing returns when you're adding motors to a chassis, not only because of the fuse on the battery, but also because of its internal resistance. There's only so much power you can pull from an FTC battery at once, and that means that as you add motors, you don't necessarily add a full motor's worth of power to a mechanism. This is still definitely more power than 2 motors, but it's not quite twice as much power like you'd think you'd be able to get out of this system. These motors are all mechanically linked together with 60-tooth gears. They are driving some 8mm pitch chain, which is then driving a shaft that the winch pulley that drives the cable on each of these systems is mounted to. Now, it's nice to have both of these slide systems mechanically linked together and strung up, because it's a little bit harder to create a very rigid connection between these 2 slide systems because they're further apart than they are on the Blue Team's robot. This also gives you some extra reliability because it means this system will still drive up and down even if one of these cable systems fails during a match. I think it's overall a pretty good idea, but it does add some complexity in that you have to match these systems pretty closely for it to work as you desired. On the other side of the robot, mounted to an 1121 series low side U channel, is the Red Team's scoring mechanism. It's based off a virtual 4-bar, which is a permutation of a 4-bar linkage. Most commonly in robotics, we use 4-bar linkages as a method of creating a lift. This is a really simple example that's built out of 2 bars of one length and 2 longer bars of another length. It's important that those pairs of bars match the lengths for what we're talking about today. We then add a joint, in this case that's an M4 screw, that allows each of the corners of that linkage to rotate. To use this as a lift, all we have to do is drive one of those joints up and down, and we've got a nice, pretty compact way to move something up and down. A critical component of a 4-bar linkage is that the opposing bars in the linkage stay parallel. This is really sweet because you can mount this first bar to your robot, mount a scoring mechanism to this bar over here, and that scoring mechanism will always stay at your desired angle compared to your robot. A virtual 4-bar does a very similar thing, but instead of 4 bars, you've got 1 bar and some chain. Specifically, these 2 shorter bars are replaced by chain. Taking this example here, we've got 1 sprocket that's mounted to the structure of our scoring mechanism. That sprocket stays solid and doesn't rotate. We then have another sprocket that's mounted to our scoring mechanism, and as we rotate this bar with this servo, that scoring mechanism stays at our desired angle relative to the frame of our scoring mechanism. This allows us to keep a cone always vertical in the scoring mechanism and allows us to score from different locations on the field. Let's talk about the intake and scoring mechanism on the end of that virtual 4-bar. It involves 4 gecko wheels. The front 2 of these gecko wheels are driven by a super speed servo that is on a 2-to-1 overdrive. It's running about 400 RPM. When we drive this front roller over a cone, it will pull that cone up against the unpowered rollers in the back, and by driving this servo and applying torque to these wheels, we hold that cone in place, and we can then use our virtual 4-bar to rotate the cone around the center of that scoring mechanism. Because this scoring mechanism is all mounted on our lift, we can lift it up, score out the back of the robot in some situations, or more commonly score out the front of our robot by just driving those wheels backwards. This does give them a lot of flexibility when compared to the blue team, but it requires more robot action to create that scoring mechanism. This has ups and downsides, and when driven well, can end up being faster in some situations. We're really happy with how both of these robots turned out. If you have questions about these robots, other parts of what we sell on goBILDA, or ways we support FTC teams, make sure to send us an email over to tech@gobilda.com.